Good morning, students. And today we'll be working on BERT, which is a super powerful model that is proposed in 2018. And a lot of embeddings like BERT, sentence embeddings, and also BERT score and SimCSE is based on this BERT, right? So it's actually a very, very powerful model. So let's see what we'll be doing today. So first, we'll be loading some data, pre-processing, and the main part of this tutorial that we'll be coding from scratch is basically data loader, right? In which we have to do a lot of pre-processing so that we got the mass data that we want, right? By the way, before I say anything, this is some code that you shouldn't use in the real world. It's mostly for educational purpose. Is coding BERT from scratch, but in practice, you may want to load the pre-trained model right away and just use it from the Huggingface, right? That should be the right way. But this tutorial mainly try to bring you to understanding how BERT is actually coded, right? And once you have faith in BERT, you understand truly, then you will have an ease in mind, right? The next thing we'll be covering is a model, and I noticed that a lot of these things are basically the same thing as transformers tutorial, right? So I will not be coding a lot of this, but the main thing you have to note is that BERT use only the encoder. So if you imagine the transformer, there's a two sides, right? In BERT, we only need this left side and extra linear layer. That's it, right? And so a lot of the code is already coded to make this tutorial not overly long. And then maybe I can go over them slowly, right? And yep. And then the training and then inference. Please note that in inference, seems that since our data set is very small, right? Then we won't see very well the good results. For example, maybe I can open this. So these are the tokens that we randomly mass, and it seems like it's trying to predict always the same word, right? Simply because my data set is simply like a one-page document, which may not be enough to train this huge model. Yep. Great. So without further ado, let us start working on this. So we're gonna do import math, regular expression. This random library will be used for randomly picking the mass tokens. Yep. So those are the libraries we'll be using, mostly very basic one. So for the data, you can basically load anything. So let me just show you the data I have, and in which I did not push to the GitHub. Is basically it looks like this, right? In which is a long passage, and but actually it's very short, like that, right? So it's actually not enough. But so basically, what I'm trying to say is that you can use whatever you want, but that is what I used, right? So feel free to use anything. So firstly, I'm gonna use SpaCy and do simple tokenizers. All right. All right. So make sure that we got this. Okay, no such fine. Okay. Okay, I got it. So now we have successfully load the text. Now we can maybe use some NLP to tokenize it, right? So I think that's it for the data. All right. So now we can go to the pre-processing, and I'm aware that there's so many ways in tokenizing these tokens, and we can just also use the idea of software tokenizers. But here, let's keep it simple and just use SpaCy. All right, and we're gonna do that. All right, so in basically once we insert the raw text into this SpaCy framework, then we got the tokenized doc, right? We have doc.ends, doc.sends, right, etc. So we can do doc.sends, all right, and right, so you can see that you can do that, right? So once we have this, we can also definitely capture those sentences. Now, what I want to do is a lowercase and clean all the symbols, all right? So here is where I gonna use regular expression, okay? X, so for X and sentences, so for each of the tokens in the sentence, what I'm gonna do is I'm gonna convert each of the text to lowercase. And this is basically things that is this is provided by, this key is provided by SpaCy. And further, I can clean all the samples in all this text. So if any of these characters follow this list of symbols, then please kindly replace them with that. All right. So that would be probably something we can do, and I think we don't need this. Yep. Okay, I understand this. Okay. Give me 1 second. No, I think this is fine. Yep. Okay, great. So now we got a very nice text. So let us take a look. And we can see that everything is lowercase. So that it won't affect our masking. Like if it's predict became and suddenly this is a big B instead, then that would not be nice, right? That's why in BERT there's something called uncase, right? And case. Okay, so I think we are pretty much okay now for that. Let us now make some vocaps, right? Right, and basically numericalization. So we're gonna do word list equal to list list of the set of the unique words, which is basically dot join x dot split, right? So what is this trying to do is basically uh, uh, splitting this guy into based on space, and then join them into a list, and then we just take the unique words out of this list, and then we again apply the list because this set turn it into some kind of generator or something, right? So we want to convert it back into list. So we're gonna do for iw and enumerate word list word to ID. We're gonna reserve reserve the first 0 to 3 for something like CLS, etc. Like padding. So we're gonna start the index at I plus 4. All right. Okay, I think I forgot something, right? Right here, what I want to do is a word to ID equal to so I want to create pad, and that is 0, and COS, and that would be 1. This is by the way, you don't have to like confuse why it should be 1, 2, 3. It basically can be anything, right? But you must have these tokens, but you can put this as 2 and this one as 1. It doesn't matter, right? But always remember what did you put, all right? Because later on, for example, for padding, you have to do some attention mask. You don't want to pay any attention on this padding, right? And for CLS, you want to apply when you predict the tokens, like whether it's the next sentence or not, you can use this token, right? Instead of the whole thing, right? So you have to remember what did you use. The word is equal to I for I, comma W, and enumerate word to ID. For cap size equal to length of word to ID. And of course, we can actually list all the tokens. Token list. Now later on, we're gonna use this anyway, right? So for sentence and sentences. For word and sentence dot split. All right. Well, sentence and text. Word to ID word. All right. Token list dot append AR. All right, so now we have so basically what this does is that we loop through all the words and in the text, and then we start the word to ID from the position of 4, and then based on that we just enumerate that, and then just create that word to ID and ID to word, right? And then the next thing what we want to do is we will be creating a list of tokens, and just for the sake of trying to see whether it works or not, right? So maybe we can take a look at some sentences, right? So those are the sentences, right? And that of course we can also take a look at the token list, and this is a huge token list, right? And then what we can do is maybe we can do some ID to word to check whether things are correctly done or not, right? So we can do for tokens. So it seems like there are a couple of lists, right? Each of them is sentences. So we can try maybe the first list and maybe print, let's first print tokens. Okay, and okay. So now we have some tokens, and it seems like something. What we can do is maybe ID to word, and we put it into the lookup dictionary, and seems like our ID to word is working very well, right? And just to make sure our word to ID is working too, we can put like that, and yep. So it seems like things are working very well. Great. So with that test, we don't really need this anymore. We can comment out, and because what we really need is this part. Great. And so I think that's it for the pre-processing. The next step we want to do is on the data loader. So in the data loader, what we want to do is we want to create a series of pre-processing. First, we want to add COS and the separators, right, between two sentences. So we have to randomly pick two sentences, right? And then so firstly, I need to explain that in BERT, the first thing you want to do is you want to mask something randomly, 15% of them, and then predict them accordingly, right? But there's a hidden second task of the BERT, which is that you need to predict whether this sentence is really followed by this sentence, right? It's called next sentence prediction. So that's why you have to send in two sentences, which is supported by the SCP. In that case, you have to put some segment embedding, basically to tell the model that this is the first sentence and this is the second sentence. The cat is walking in 0, 0, and the dog barking is 1, 1, 1. For the masking, you have to mask 15%, but in this 15%, 80% is replaced with mask, 10% is replaced with random tokens, and the rest 10 is left as is, right? So here we will be specifying something called max prediction that doesn't allow it to predict more than this 15%, right? And finally, we need to add padding so that we will have so because the transformer cannot randomly accept any length, right? As you want. So you want to specify the maximum length, and then if that sentence does not reach that number of length, you just add padding, right? So that is like the idea. Here, the next thing what I will be doing is that there will be a variable called positive and negative. It's simply used to keep track of whether positive refers to two sentences that really next to one another. And I don't want to be like too many positive and too many negative. Maybe what I can do is maybe half, right? That would be probably a good idea. Okay, so without too much explaining, why not we just do it and maybe you guys can understand much better. So let's imagine we have a batch size of 6 and so and then 5, right? And so this is basically calculated roughly of 15% around, right? But of course, okay, let's say like this, you in a sentence you don't want to mask like too many tokens, right? So you can set this as a hyperparameter to say that even though it does not reach 15% yet, maybe you can you can set this threshold, right? So so this is entirely like optional whether you want to do that, right? So this is something you want to play around. And the max length is 1000. All right. So this is the maximum length that my transformer will accept. That means that the all sentence will be padded, right? Actually, I think this is way too long. Maybe I can play around with it. Maybe if I reduce this, maybe my inference maybe can be better. Yep, I don't know. Yep, you guys can try, right? So those are some parameters that you can play around. Okay, great. So now let us work this out, right? So we're gonna create a function called make batch, and batch equal to that, and positive equal to negative equal to 0. So we keep count, right? So why the positive is unequal to batch size divided by 2, negative batch size. So we keep doing this until we got half. All right. And so each batch, what we want is that we want exactly half that are really the next sentence, and or maybe negative. If the negative is already half, then the positive should be half already, right? So then what we can do is so there are a couple of things we want to do here, right? So the first thing we want to do is randomly choose 2 sentences, right? And then what we do is token embedding, apply, add CLS, and SAP accordingly, right? And then in the second part, what we want to do is we want to create a segment embedding so that we know which sentence is 0 and 1, right? And then in the third part, what we want to do is actually masking, right? So this is the probably the main part of this tutorial. And then the next part, what we want to do is padding to the maximum length, right? So padding is super simple. We just add 0 because 0 is the token ID of that. And we also need to pad the mass tokens to the maximum. So this is the padding, pad the sentence, right? So there are 2 things we have to pad. We have to pad the sentence, and we also have to pad the mass token. So this is like the input, and this is the like the output. And we want them to match, right? You can imagine that if transformer accept 1000, it will output 1000 hidden representations, and maybe you just want to get the certain position, right? Which you care about those predictions, right? But in any case, the label should be the same length as the input. And then check whether it's positive or negative. And then this number will be affecting this. And finally, return the batch. All right. So let's do this together. And all right. Sorry. So firstly, let's randomly choose 2 sentences. Guys, please give me one second. Let me drink some water and I will be back. Okay. So now I'm back. So let's first randomly select two tokens. So I'm gonna say two sentences. So I'm gonna say tokens B equal to rat range. And that just simply choose whichever sentence I have. All right. Yep. And this will give me two index, right? Selecting the sentence. And then now what I can do is retrieve the tokens of those two sentences. Tokenless. Tokens A index. And tokenless token B index. Okay, now I understand why myself need this. Can you guys come back here and make sure that you don't comment this out, because I first thought myself in the past just simply want to check, right? But actually I actually use this tokenless. All right. So now we can come back and we can make sure that okay, great. So now I retrieve all the tokens of this sentence and that sentence, right? Now what I can do is I would say that input IDs is equal to word to ID of this token called CRS, which it will be one, right? And then plus so I have to be careful here. All right. I think I am correct. Yep. Plus. Okay. This is that. And that should be okay. Yep. Plus tokens A plus word to ID. And what we want here is sub, right? And then plus tokens B plus word to ID. Sub. All right. And I think here I need the bracket. Yep. All right. So that is so basically what I'm trying to do is add a CRS. All right. And then the tokens, and then the separator, and then the second sentence, and then followed by separator. So those are the input IDs. And if you're wondering why I'm using this, because once we switch to Huggingface, these are the exact term that they use, right? And actually this tutorial is very nice that it allows you to actually also understand internal mechanisms of the tokenizing process in Huggingface. For segment embedding, what we can do is segment ID is equal to 0 times 1 plus length of tokens A plus 1 plus I want 1, and then multiply with length of tokens B plus 1. All right, and so what you're gonna do is you're gonna add number of zeros equal to 1. 1 here is basically from the CRS, and 1 is this one, and all of this will be 0, right? And I don't know why, but if you look at the actual paper, the sub is also considered as the first sentence. So that's I guess it makes sense, right? Because this is the part of the second sentence, and then this plus 1 is basically this guy, right? Great. So that is segment embedding. Now we can go to the masking, right? Which is the main part, right? So what we're gonna do is we're gonna do the first of all we have length of the input IDs, right? And we want to make sure that we get 15% of that and mask them. And definitely we have to round them appropriately to maybe up, and then we're gonna put it in, right? And of course, we don't want, what if it's like 0, right? Then we want to make sure that we always at least mask 1, right? So we put a max here. And then finally, we don't want to exceed the max, right? So we want to take the minimum of this 2 thing, right? And then finally, we're gonna call this end predict. That is the number of things we want to mask. Yep. So yeah, and then what we're gonna do is, what we want to do is now get all the positions, excluding CLS and sub, sorry, and sub, and sub. Yep. So what we're gonna do here? So basically, before I can mask them, I need to know the position, right? In which which one I'm gonna do, right? So here, what I'm gonna do is I'm gonna say for I token and enumerate input IDs. And I want to get this I, right? This is the position. Only if token is not equal to sorry, or to ID CRS and token also not equal to word to ID of sub, right? And so I think that should be okay. Yep. And based on that, we should be able to get this I. This is the positions, right? And then we're gonna call that candidates for masking position, right? So these are the candidates that we can actually mask, right? Hopefully that won't create any problem, I hope. Now what we're gonna do is shuffle, play some game and shuffle them, and then whoever comes first is the one that we're gonna just mask them, right? Like candidates mask position, right? And then now we're gonna seriously mask them, right? So mask tokens, mask position equal to that and that, right? So this gonna keep track which token I mask and the position. So this will be like, you want to only get the output when I predict, you want to get only the output from this position. And when I calculate the loss, you want to compare the loss with this token, right? So that's why we need to have this 2 guy here. And now we're gonna loop, simply loop and mask accordingly, right? And whatever is coming first in this shuffle list will be masked, right? So for position and this candidates thing, and we don't want to have that many, so we're gonna only take and predict, right? So this is the one that we already decide how many we want. Then mask position dot append. So we already know which position we're gonna mask. We already know which token we're gonna mask, because this is the what that we have is dot append. Sorry, input IDs of this position, right? But now we have to, we already know what we're gonna mask, but we haven't actually perturbed the real sentences, right? So what we're gonna do is if random is less than 0.1, right? So this is basically 10% replaced with random token, right? So this random cup return a number between 0 and 1. So there's a 10% probability, right? In this 15% tokens that we will be simply replacing any random token. So we can retrieve any random tokens from the vocab size, and then we just say that precision that precision will be word to ID. Sorry, ID to word index. All right. So first we convert. Sorry, this ID to word, and we got the word, and then we convert that to the real ID that is in using this word to ID. All right. And then what we're gonna do is otherwise we have 80. We're gonna have a 80% chance replace with sorry, with mass. Right. So now we say input IDs post equal to word to ID. Right, and that is the mass. But then we also have the 10%, right? Even though we already remember which position we mass and the mass token, we're not going to perturb it and try to fool the model that, hey, you need to predict that position, right? But actually we did not change anything, right? So that is that. So yeah, I think that is the major part of the BERT. And then the rest is simply padding to make sure that so padding the sentence will help us to make sure that the transformer exactly the same length. And also the padding will allow us to, when we do the attention, we have something called attention mask, in which it will know that which part it should not pay attention to. All right, so now we're gonna say npad equal to max length minus whatever is in that. So now we know how many we need to pad, and then the input IDs dot x10. X10 is not like a pen, right? Otherwise you have many like let's time and pad and segment IDs. Yeah. So for the segment IDs, we just simply also pad with 0. Yep. Yeah, it's a little bit confusing. Like for segment ID, we have 0 and 1, and then we have another 0, but because we only care about the first 0 and 1, it should be fine. So we just pad anything at the end as 0 anyway. And then we're gonna pad the mass tokens. Again, if you don't understand this, when we input to the transformer, we have like 1,000 tokens, right? And when we pass through the transformer, because it's basically linear layers, you will get exactly the 1,002. So then this 1,000 need to compare with some output, right? So that output would be the mass token. So it should be the same length. But of course, if output is 1,000, this should be also 1,000, right? Then npad equal to max mass minus pad. Minus and predict. And then so we know how many we need, and then we're gonna do mass tokens dot x10 0 multiply npad, and then mass x10 and pad. Okay, so that is the paddings. Now, the last thing we want to stop this loop is the positive and negative, right? So what we're gonna do is if tokens, so how do we know is next sentence really? Well, it's super easy, right? If plus one, then that is equal to tokens B index, right? Then that is like, then and if positive, it's still the batch size less than 2, then we can still keep adding. And then we can say batch dot append. What we need to have for each batch is the input IDs, segment IDs, mask tokens, right? So this is like the input. This is like the output. And the position is needed because you only care about the prediction in this position, right? So you don't get all the transformer will output like 1,000 tokens, 1,000 representations, right? You don't want to look at all because you only mask like 15%. So you only look at this position. And then finally, this is like, is really the next, this is really the next sentence, right? So this is the label for the second loss. And then of course we're going to do positive plus equal to 1. And then we're going to do the same for the negative effect. But let me just check what is wrong here. Okay, I misspelled this token. Okay, so I should say actually. Okay, give me 1 second. Can I? I'm just gonna do command D, make sure that I only have 2. Okay, and then say tokens A underscore index. Okay, great. And then that should allow this should be correct. Okay, and then next thing is elif tokens A index plus 1 is not equal to this guy. Then I think is and then as long as negative is less than batch size of divided by 2, then batch dot append. And what I'm gonna do is simply copy this and put it as false, right? And then negative plus equal to 1. All right. Yep. So I think that's really it. And we can try to run this and hopefully there will be no errors. And I would invite you to try to go back and try to decode them and see what is inside each batch. But here I'm just going to make sure that it runs and that the length of the batch is 6, right? According to my batch size. And of course, we can try to see whether we really got this input IDs. So maybe I'm gonna just deconstruct this one. So I'm gonna say that please convert everything into long tensor, right? And treat this as each of them. All right, and this one gonna be input ID. Sorry, segment IDs, mask tokens, mask position, and is next, right? And so what I'm trying to do is for each of them, zip them. By zipping them, you'll get like in this, putting them like stacking together 6 of them, stacking together 6 of them like that, and then put them all into long tensor. This is like very common operations. Why do we need to stack the input IDs together? Simply because PyTorch expect that. They don't expect like 1 by 1. They want this one 6 together, 6 together, 6 together, something like that. But currently I'm just trying to print, right? So I think we let us try whether there's a it's okay. Okay, so type errors is not a sequence. Give me 1 second, and then I will. Okay, How about you guys give me 1 second and I will be back. Yep. All right, so I found out the problem. The problem seems like right here. Yep. So I don't have to actually, because this is itself already the token, the ID already. So we don't have to enclose it into a list, right? Then that this will be ID, etc. Right. So let us try this again and hopefully no problem. Right. And now what we can do is we can maybe print all the shape here. Right. So now we can have something. So we have 6 batch, and each of them is 1,000. Right. So we have 1,000 input, 1,000 segment, and we have 5 tokens that we actually mask and their position. And of course, if you want to actually print the position, you can print, right? So these are the position in which it masks for the first sentence, second sentence. Of course, you can also print the tokens, right? And if you wonder what are they, you just use ID to word, that should be fine. And then for the next sentence, it seems like we got positive and negative, negative and positive sentence next to it. Great. So it seems like we are doing great. So that is the data loader, right? So the for the model, then we have embedding, and embedding is simply having the token embeddings plus the segment embeddings plus the position embeddings, right? So basically, we just create them accordingly and then just add them up. Very, very simple. And a layer norm is applied. We have also attention mask. Basically, for example, if we are doing self-attention, Q and K will be the same one. So they will also have the same padding. So we just say that if the data in any part is equal to 0, please create that mask. So this mask will be having 1 in that location. And then we just have to create another dimension here using unsqueeze, and then create this mask as this shape. You can check whether this shape is correct, right? Because when you do attention between 2 sentences, it's basically this sentence pairwise another sentence, right? So the attention will be in this shape, and we want to create this kind of mask that if those one thing, we just put, if anything that hit 1, we just apply like attention of minus infinity, for example. So yep, so this is just an example that it looks like this. So this is some testing. The rest is very similar to transformer, but again, what we do is only the encoder. We don't need the transformer, right? We don't need the decoder, right? So this is the multi-head attention and the position-wise part. And also this is the scaled the product. So this is a QKV, QK multiply with V and then softmax, right? And then we fill the attention, we fill the scores, attention scores based on this attention mass with a minus infinity thing, right? And of course, now we have multi-head attention. And again, this follow my previous transformer tutorial, right? In what you do, you create a QKV and then split them into heads and then do scale the product and then get the context, and then you pass through the linear layer and then layer norm, right? So, and this is basically skip connection. So basically like 90% similar to what we already studied in the transformer. Yep. Positional position wise feed forward network is simply two linear layer. Finally, when we put them together, it simply look like this, in which we get the output, right? And as you can see, once you pass through a lot of layers, right, eventually the output will be the same length as, it's basically still 1000 here, right? So what you want to do is, firstly, for predicting the next sentence, what we're going to do is we're going to get the zero position. Basically, we use the representation that is from the ZOS, pass through a linear layer, some activation, which is simply 10, and then just add them to classifier. And the classifier is simply the linear layer. So that is predicting the next sentence. For the mass token, is a little bit, if you're not familiar with Python, this may be a little difficult. But what this is that we get the mass position, and then we manipulate the shape just so that we can match them to the output. And then we use the function called getter. And getter seems like a difficult, but the intuition is simply say that, hey, please retrieve any number from the output of this position. That's it, right? And then based on that, we pass through a linear layer, some activation function, some layer norm, and this is the prediction, right? And then we just pass through a linear layer, right? The decoder is simply a linear layer, and then which will predict all the vocabs, right? So if we have 5 tokens that are masked, this will be 5 tokens. Yep. So yep. And then the training is very basic training, not much things. One thing you may want to see is that the loss function is basically with the mass token, right? If you don't see that already, yep. And we have also 2 loss, and that is the sentence classification. And then the real loss is when you add them together, right? So then you will have, so you can see that loss is decreasing. And finally, in the inference, what I'm doing is simply creating a batch, right? And then just try to dot max and try to retrieve the answer, right? So that is that. Okay, great. So I think I hope I did not make the tutorial too long. Of course, I go very quickly over here, but if you're not familiar, maybe you want to go back to the transformer tutorial, but mostly it's not so difficult. Yep. I think that's it. Yep. Thank you very much, and see you next tutorial. Bye bye.